Hi everyone, welcome to my talk. My name is Boda Liu. I'm a postdoc at Rice University. This project is a collaboration with Professor Cinti Li. Let's start with this picture of Mount St. Helens eruption in 1980. Half of the volcano cone is destroyed. 57 people were killed. In another example, the eruption of Mount Pinatubo in Philippines in 1991, it kills 300 people. So silicic eruptions can be very disastrous. We geologists are motivated to investigate why this happens. We need to learn from past eruptions and look underneath the ground. Many of us may know that silicic magma is usually associated with mafic magma. Using these Hacker diagrams on the left, work argues that the high silica rhyolite could be produced by fractionation of mafic magma. The picture on the right, taken by Davi and others, shows the dark mafic enclave found inside rhyolite. The authors argue that the intrusion of mafic magma triggers the eruption of silicic magma. This observation suggests that the mafic magma could have controlled the production and eruption of silicic magma. Therefore, we can ask a scientific question: how does the reservoir of silicic magma grow? We want to know how fast is the magma intrusion and how is the melt extracted from its source region. To model these processes, we envision a simple marsh reservoir system consisting of a silicic reservoir underneath the ground and a large crystal-rich source marsh underlying the silicic reservoir. The typical depth of the silicic reservoir is 6 km. The model is one-dimensional. The horizontal area is about hundreds of kilometers. The relatively mafic magma is trapped in the interstices of the crystal-rich source marsh and needs to be extracted to replenish the silicic reservoir. We notice that for the mafic magma to evolve, the reservoir needs to undergo cooling and crystallization. Therefore, we formulate the thermal balance equation for the silicic reservoir. The cooling rate is controlled by three terms. One is the heat loss through the overlying crustal layer. The second is the advected heat associated with replenishment. The third is the latent heat released by crystallization inside the silicic reservoir. A fundamental assumption here is uniform temperature for the silicic reservoir. As long as the crystal fraction of the silicic reservoir is low, the magma should convect, and most crystals should be entrained in the convecting magma. Therefore, the uniform temperature would be a valid assumption. This thermal equation of silicic reservoir could be coupled with the heat conduction equation of the crustal lead and form the complete system. Before solving the full system numerically, we can get some insights from analytical results. If we balance the three terms on the right-hand side of the thermal equation, we can obtain the steady-state temperature of the silicic reservoir. The temperature of the input magma is assumed at its liquidus. There's a small correction term for the latent heat. It is the reciprocal of the Stefan number and approximately 0.5. We plot the steady-state temperature as a function of J for different values of heat loss flux Q. The x-axis is the replenishment rate J. The y-axis is the steady-state temperature. Lines with different colors represent different values of heat loss flux. We found that a minimum J is required to prevent the silicic reservoir from freezing. If J is infinite, the magma reservoir would be at the liquidus temperature of the input magma. For larger values of heat loss, the minimum J needs to be higher. To the first order, the heat loss through the crustal layer is proportional to a linear geothermal gradient. The hydrothermal system, like those in and around Yellowstone, can significantly increase the effective thermal diffusivity, therefore requires higher minimum J. Here we show the results of heat conduction in the crust. As hot magma starts accumulating at the base, a sharp temperature gradient produces high heat flux at the beginning. The basal flux then decreases as the geotherm relaxes back to linear. In this slide, we solve the full time-dependent system. We consider two cases of replenishment in the left panel. One has constant J of 0.3 meter per year. The other has replenishment rate decaying to a base level. The resulted thermal evolutions are plotted on the middle panel. In the case with constant J, the temperature reaches a high steady state. The deficit at the beginning is due to reheating of the crustal layer. While in the case with decaying J, the temperature decreases, as expected from the decreasing ratio of J over Q. The crystallinity of the magma reservoir and the silica content of the residue melt are shown on the right panel. The case with constant J produces a residue melt that is very similar to the input mafic magma. On the other hand, the case with decaying J produces high silica rhyolite with more than 50% crystals. Therefore, the growth of the magma reservoir is very fast at the beginning, capable of accumulating 200 km3 within 10,000 years, and then the growth rate slows down. It is important to note that at the steady state temperature, the silicic reservoir is still growing. The melt volume of the silicic reservoir increases at a fraction of the base level replenishment rate. The steady state crystallinity of the silicic reservoir depends on the ratio of base level replenishment rate J over the heat loss flux Q. So what is the reason for J to decay? Recall that the melt is extracted from a crystal-rich source marsh. We can calculate J as buoyancy-driven Darcy flux. Using a suitable permeability model, J scales with the cube of the marsh porosity. Therefore, fast J at the beginning reflects a temporarily high marsh porosity. As melt extraction reduces marsh porosity, the permeability decreases and J slows down. We suggest that the arrival of deep-seated mafic magma pores at the bottom of the source marsh rejuvenates the marsh, resulting in temporarily large marsh porosity and a fast melt extraction rate. The perturbation of J causes the existing silicic reservoir to erupt. After the eruption, a new silicic reservoir would be gradually rebuilt. So these steps 1, 2, 3 could repeat in such a way the volcanic cycle may be regulated by pulses of deep magmatic activities. That's all I have for today. Please don't hesitate to contact me. Thank you for your time.